I'll be describing the large-scale simulations of the solar corona. And Gabor Toth and Yushi, his postdoc, have been working on the simulation and cell MHD embedded model. This is being done at the University of Michigan, where we are done a great deal of work on developing modeling for coupling a number of different models together, going from the sun to the lower corona, actually from the convection zone to the solar corona to the upper corona, where you can drive an eruption, a coronal mass ejection, propagating out through interplanetary space, and it couples then to an inner heliospheric model, which then can couple to the global magnetosphere, and from there it can couple to a whole range of models which couple our atmosphere, from the plasmasphere, ionosphere, radiation belts, the whole sphere are coupled together. Earth magnetospheric system. So the idea is we can couple all the entire of weather from to that blast wave, that coronal mass ejection, shock wave, ejected material propagating through interplanetary space and impacting the magnetosphere and the impact that it has there in the Earth environment. So to begin with, I'm going to be describing the work by Gabor Toth and Yushi Chen with the PIC model. So coupling of a PIC, one of these, I know. Excuse me? So the MHD model is shown on the spherical grid, and the PIC model is shown on a Cartesian grid, and they overlap. There's a should be exit case. This is an area of let me adjust this. It's flopping around a little bit, and then I think it'll be okay if I get this pinned up higher. Is that? I think that's. Does that sound good now? Is that okay? So we have this region where these two models, and so there'll be a region of reconnection MHD model, and this is connected to. So there'll be some in nuclear activity. This is where there's flux breaking to capture the kinetic scales where that process is going on. And MHD doesn't capture that physical processes, but the PIC simulation can capture that physics. And so the idea is it's impossible to model the entire global magnetosphere with a PIC code. It's simply way too expensive, primarily because of the as well as the temporal evolutionary scale. The time step is so small associated with the evolution, particularly with the electron. So we do in a regional way, where the PIC model is embedded, shown here. And so this is coupled through a region of ghost cells surrounding the PIC model. So the information, they start out with the same initial condition, which is generated in the MHD model. That's used to populate the PIC model. And then once that begins to evolve, information from the PIC model propagates out into the ghost cells and then is pushed out into the MHD model. So this is basically the way in which the coupling is performed. So this is a system of equations that are being solved. So in ideal MHD, we basically have a fluid description with a fluid velocity evolving with a magnetic field. We solve an induction equation, shown here, Faraday's law. In addition, of course, the Maxwell stress tensor term is in the momentum equation. And so you have a coupled system of the magnetic field and the fluid. The right shows the equations being described for the PIC model. And in place of U here describes the fluid velocity, where on the right here in the particle in cell, we have the velocity is with a letter V, illustrating the actual velocity of an individual particle. So these are individual particle velocities and evolving the position of these individual particles. And it'll be 256 particles typically in each cell. And so you're actually solving for the particle distribution described within each cell with this number of particles for both protons and electrons. In this case, too, we actually solved the full set of Maxwell's equations, including the displacement current in this equation. And then for the PIC simulation, the electric field includes the the Hall term, the J cross B Hall term here. So that is a much more dynamic system of equations. There's many more wave modes allowed. So you have Whistler waves, for instance, as a result of this, and a much richer physics. And so the time scale associated with this evolution is much, much shorter. And so this is going to completely dominate our computational costs. It's going to be the particle and cell simulation, even though it's a tiny fraction of the volume of the space being simulated. So basically, showing the physical parameters. And so in order for the PIC to be able to work, even with the enormous computational resources we have on blue waters, we still have to adjust the ion inertial length and increase it to 1/16 of an one-sixth of an RE to be able to resolve it and adjust the ion to electron mass. Instead of being a factor of roughly 1800, we reduce that to a factor of 100, which is pretty typical for these particle type of simulations. And this is going to be shown in a small box, and this is going to be on the front side of the Earth where the solar wind is impacting the magnetosphere, causing reconnection to occur between the solar wind magnetic field and the magnetospheric magnetic field. So the MHD domain is much larger, extends out to 224 Earth radii behind the Earth, extending quite a ways in front of the Earth. And we have this imposed solar wind, which is driven from observations. So there's a satellite at L1, which is between the Earth and the Sun, at about 1% of the distance of the way out from the Earth. And so that's roughly about 1 million miles in front of the Earth. And that basically acts as a solar wind monitor where the information can be picked up on the condition of the solar wind. And that is used as input into this model. So this is what the PIC simulation looks like. This is the scale. This is showing the side of the magnetosphere, basically on the nose of the magnetosphere, which is being impacted by the solar wind. And you have this area of reconnection going on. And so this is the side here on the Earth side of the impacting solar wind, and it's coming in and it's forming a current sheet between these two flux systems. And so you have a relatively little guiding field. The magnetic field is coming in opposite directions. And this is an area of magnetic reconnection forming the island at this point. So this is what's called a flux transfer event in the magnetospheric community. It's producing this flux rope here, which I'll show three-dimensional images of it in the next frame. And so these plots here are showing the structure of this magnetic island on this dotted red line, which you can barely see, but it comes from here. This system goes through this magnetic island and comes out this side. So this is all done with the PIC simulation, which captures all of the kinetic physics associated with the flux breaking and the reconnection process. So this is showing the structure of the magnetic field component, the rotation, the BX component, and the BZ, and then there's a field component out of the plane. So the thing that we're pointing out here is this is showing the total magnetic field strength. BT is the total magnitude of the magnetic field, and it shows a significant magnetic field strength on either side of this island. And of course, it's very weak in the center, and so that's shown in this plot here. Again, you see the two sides of the flux rope, a depression in the middle, and then two areas of weakness on the outside of it. And this is a comparison with observations from a similar flux transfer event, showing the rotation of the field components and the structure of the overall magnetic field strength. So this is the first time that we were able to incorporate this type of a PIC model and resolve the physics going on this scale and actually capture the physics of magnetic reconnection, the kinetic physics on a global scale model to get the processes of flux breaking and how the process of reconnection occurs. And this is really significant because this is a fundamental process in space and astrophysics in terms of how magnetic fields are rearranged, how the energy is released, how flare events occur, in this case how magnetic flux is transferred in the magnetosphere that then accumulates in the tail where it can reconnect and ultimately drive the geomagnetic storm. So this is a three-dimensional representation of that simulation, and this is showing the formation of that flux rope in this flux transfer event, and this is at the nose of the magnetosphere, and you see this form and they begin to twist and turn, and then you get the formation of a second and the interaction of these flux ropes. So one of the really interesting things you have with particle and cell simulations is you get a lot of kinetic physics out of this, and you get different modes of instability. And this is showing the development of a lower hybrid drift instability, and this is showing current sheet located right here with this black line is where the two flux systems are coming together. And these islands are areas, so this is showing the electric field, and this is showing the development of the small scale structure of intensified electric field where this instability is occurring. And this is showing and density and the electron velocity. So this compares very favorably with observations. And then this is another simulation using this embedded PIC model. Again, this is now showing the global magnetosphere. What I just showed before was a region right here on the nose in the magnetosphere where this driven reconnection was occurring. As this reconnection occurs, it allows the magnetic field that's on the front side of the Earth to peel back and be carried back in the solar wind. And so you get is a lot of open magnetic flux in the. And once this builds up to a critical level, you then get reconnection here in the tail, which then drives the geomagnetic storm. So this is the fundamental process by which this occurs. So a summary of this part of the talk is that you can simulate the generation of these flux transfer events, the formation of these flux ropes that matches the observations, the growth of these flux ropes in interaction, the way they twist and turn, and these multiple flux ropes can interact. And we get the overall structure, including this anticorrelation, basically a buildup of dense plasma within the core of that flux rope. And it matches the observations and also reproduces the lower hybrid drift instability. So anyway, what this was supposed to show was a large-scale eruption of this feature. So basically this part, so this is an observation in helium-304, which is showing cooler temperatures at the chromosphere. So this is why you see all this structure in the lower atmosphere. This is the chromosphere, which is being highly structured by the magnetic field. And this region here in the limb is a region of an active region where there's intense magnetic fields, and this area can erupt quite dramatically, forming this loop extending off the solar limb. So these eruptions have been observed and been known since the late 60s, so roughly 50 years, and the exact process by which they occur still remains elusive. So they occur, the energetic eruptions occur primarily from solar active regions. So this is an image of the magnetic sun, and this color represents the magnetic field strength on the disk of the sun. And so the red to blue are opposite magnetic polarities. And so this is a region of intense magnetic fields where you have kilogauss magnetic fields and sunspots. And this is a primary region where the magnetic field erupts. And this is a close-up of an active region showing the radial magnetic field strength at a gray scale. So positive coming out of the screen, black is negative going in, and the arrows are showing the direction of the horizontal magnetic. So this is known as a vector magnetograph, which we can produce from the spectral lines and from on splitting. So we can infer the intensity of the magnetic field in the sun, and this is the region where these strong eruptions occur. So the primary focus of this project that I'm working on is to be able to simulate one of these active regions on the sun on this scale completely from theoretical constructions with an MHD model. So starting out with a magnetic field, allowing it to interact with the convection, which I'll show, and self-consistently produce this structure on the sun and actually evolve it to the point where it erupts. So this is an extremely demanding simulation because of the length scales that are necessary to resolve. And so there's very, very small length scales associated with the pressure scale height and the structure of this active region. At the same time, the distance of this is several hundred megameters across. And so it requires extremely high numerical resolution. So we developed a spherical wedge active region model with, this is the physics that we incorporate. It's important to include ionization of hydrogen and helium going through the corona because the temperature is falling off from about 250,000 degrees at the base of the model, which is at 0.95 of the solar radius, coming up to the photosphere where the temperature is only 5,000. So this shows our structured adaptive mesh. And so each one of these boxes here is 10 by 10 by 10 grid cells on a spherical wedge. And the highest resolution here is right at the photosphere where the temperature is the coldest and where the convection is the strongest. And so we zoom in here showing that structure. So this is the radial velocity, and this is showing the granular convection at the photosphere, which is how that energy is making its way out through. And then there's a hierarchy of convective cells. So the deeper you go into the sun, the higher the temperature and the larger those convective cells. So we need to resolve this structure and all the. And so this is showing the image at the photosphere on a grayscale of the radial velocity. And so this is showing the photospheric convective cells at the photosphere. And here the convective cells have a lifetime of about 5 minutes. And down in this deeper part of the atmosphere, it's about a period of about 1 day. And so this stuff is rolling over very, very rapidly at the photosphere while over a very long time scale, the field is evolving deeper in the atmosphere. And this is showing comparison of that convection with observations. And so what we're doing is we're simulating the emergence of magnetic fields coming from the convection zone, the form, and active region. So this is the first time we can do a full active region scale with these computational resources. So this is the largest ever numerical simulations. So this is showing the photosphere and showing the magnetic field strength as a synthetic vector magnetogram. This is showing the formation of the active region, the opposite polarities, the magnetic field rising up into the corona. And this is showing the direction of the magnetic field at the photosphere. And so now we've embedded that model of the convection zone into a global model of the corona, in which we can allow that magnetic flux to come up and form sunspots and actively erupt. So this is a huge advancement in our capabilities to simulate the sun, solar magnetic fields, and their eruption. So to summarize, spherical wedge active region, largest simulations ever done, 150 by 300 megameters. This is typically times the size of previous simulations. We capture the convection all the way down to a depth of 35 megameters. We can simulate flux emergence and the formation of active. On the magnetic side, we've shown MHD embedded PIC models to simulate the Earth's magnetosphere, capturing regions of space where magnetic reconnection occurs, and the kinetic physics is essential for that reconnection process. We show dayside reconnection and these flux transfer events and the interaction of those flux ropes. This is done with a two-way coupled MHD kinetic simulation. As well as we also showed reconnection in the tail region of the magnetosphere, which is essential for the driving of geomagnetic storms. And a key feature of this is how we also get the kinetic instability, such as the lower hybrid drift instability. Future work is to continue the simulations with the SWARM awesome global solar coronal model, these fully coupled simulations, continue the flux emergence, and do a coupled simulation of the convection zone with the global corona, and then to do the and to cover both magnetopause and magnetotail with both the development of geomagnetic storms. And blue waters was essential for the success of the project. Simple and easy to use, unlike the microphone. We get large scale. First, we get huge data sets produced by these three-dimensional simulations. We're able to actually transfer that data fairly readily back to our home institution to analyze it. We also have very good data storage at the facility. We can keep that, and the support staff has been very helpful in helping us get set up and run these projects. And so basically we have an order of magnitude more computer time than we have from other systems that have really allowed us to increase the scale of the simulations, as well as the complexity of the simulations. We get pretty short turnaround times, and being able to do simulations that require anywhere from 5 to 10 million CPU hours. And we also enjoy a very good software environment and the stable hardware. So thank you very much for that support.